This is an arc. An arc is a piece of a circle, not the whole thing. Could you reconstruct the entire circle from just this piece? And you can actually pause the video right now and try to do that. You could make your own little arc, find something round, water bottle, cup, whatever, trace a little piece of it onto a piece of paper, and then can you find the center? One way to do that would be with paper folding, although you could also bust out like a ruler, compass, straight edge kind of situation and try to do it that way. Okay, feel free to now unpause the video if you've either found a solution or given up, and let's talk about it. Okay, so how do you reconstruct the circle? The key is to find the center. So how do you find the center of the circle? I'm gonna open up my this thing, the Desmos construction thing. So let's make an arc. An arc, again, is a piece of a circle. So here's a piece of a circle. How am I gonna make the whole thing? Well, what I'm actually going to do is I'm going to make two chords. What's a chord? It is a line segment connecting 2 points on a circle. Since the arc is a piece of a circle, these two chords are going to be chords on that same circle if we did finish it. Next, I'm going to find the midpoint of each of those chords. After that, I'm going to make a perpendicular line that goes through each of those midpoints. These two lines cross somewhere. That point right there is the center of the circle. Hey, look, it fits perfectly. And if you're like, why does that work? Don't worry, we will talk about that. But first, I actually want to pop back out here and be like, hey, I said you could do this with paper folding. Were you able to do it with paper folding? One way to do that would be to fold the endpoints of your arc on top of each other so that they line up perfectly. And then when you do that, you get yourself a crease in the paper. The crease in that paper is the perpendicular bisector of the chord connecting the 2 points that you lined up on top of each other. Now you could do that again from, like these 2 points, for example. So I could fold my paper over again, so I'm getting, 2 more points to line up on top of each other. And, wow, I'm not very good at folding paper. I'm kind of failing. But you get another crease, that's another perpendicular bisector of a chord, you get the center of your circle, you can get out your handy dandy compass and, reconstruct it from there. I don't know if I'm very good at doing that quickly, but hey, look, my compass slid out a bit. This wasn't perfect at the spur of the moment, but look, it works. Okay. Anyway, let's jump back into the construction tool though, and if you're interested in figuring out why does this work, that's what we're gonna talk about now. If you just wanna know how to do it, well, there it is. Bye, see you in the next video. If you're interested in why does this thing work, okay, it comes down to a couple of little details. First of all, so each of these lines we made here is called a perpendicular bisector of the chord. Now, if we could prove that the perpendicular bisector of a chord will always pass through the center of the circle, then it's now obvious why this worked. Because if this line has to pass through the center of the circle, and if this line also has to pass through the center of the circle, then the point that is on both lines has to be the center of the circle. Okay, cool, but how do we prove that the perpendicular bisector of a chord always passes through the center of the circle? Well, let's prove that now. Let's make a circle. So if you take any old circle, nothing special about it, and make any old chord in that circle with nothing special about it, let's go ahead and make a triangle by connecting the center of the circle to the endpoints of that chord. Now, I'm going to tell you this is an isosceles triangle, meaning that this line and this line are the same length. Why is that the case? You could pause the video and explain that to yourself for a second here. I'll talk more about that later. The next part of the construction is putting a midpoint on the chord. Any old chord, you could always find the midpoint of that chord. Okay, and now I'm going to make a line segment that joins the center to that midpoint. We now have two triangles, and they certainly look congruent. They also look like they are right triangles. Let's say we could prove that. If these were congruent triangles, and we could prove that these were 90-degree angles, then we would have just proved that the line segment joining the center to the midpoint of the chord, and if we prove these are 90-degree angles, well, if these are 90-degree angles and this goes from the center to the midpoint, then what we're saying is the line segment connecting the center to the midpoint of a chord at 90 degrees, well, that is the perpendicular bisector, right? In other words, the perpendicular bisector, the definition of that is a bisector. It's going through the midpoint of the chord, and it's going at a 90-degree angle. So that would prove what we're trying to prove. Got it? So we just need to fill in the details. To do that, I'm gonna take a quick a quick screenshot, there we go, and we're gonna add in some numbers and letters and things. Well, maybe not any numbers. We're gonna add in some letters though. Let's name some things. So first of all, let's name the chord with its endpoint. So I'm gonna call that endpoint A and this endpoint B. And let's say that this point, let's call it D, is the midpoint of AB. So D is the midpoint of AB. Okay, so that's useful because now by definition, this length matches this length. That's the definition of a midpoint. Now, let's call the center of the circle C, and let's explain why AC must be congruent to BC. Pause the video if you haven't yet. I challenged you to do this earlier. Why do those have to be the same? I'm about to say it, so make sure you've thought of it yourself. They're both radii of the same circle, so they have to be congruent to each other because that's the definition of a circle. They are points, the circle is points equidistant from the center, so any radius is the length connecting the center to the point on the circle, and those will all be equal. Okay, cool. Now CD has to match itself, so because it matches itself, that's the reflexive property, if you care about the technical names for things. We now have a side-side-side congruence test. So let's start writing some things down. So I know that triangle, oops, actually I clicked on something over new. I don't want new, go away. Anyway, okay, so we've got, let's go with triangle ADC is congruent to triangle BDC. Why are they congruent? Because they pass the side-side-side congruence test. Now, that means that, remember, we want to focus on proving these angles are 90 degrees. Well, let's start by proving that these two angles are equal to each other. So why would this angle have to be equal to this angle? Why would that be the case? Again, pause the video and try to supply that reasoning for yourself. And now feel free to unpause the video. I'm going to explain it. Angle ADC is congruent to angle BDC because corresponding parts of congruent triangles are congruent. Okay, now I want us to justify why angle ADC and angle BDC are 90 degrees. Right, those, I guess I could say the measures are 90 degrees. Why? Why though? Again, you could pause the video and try to supply the reasoning for yourself. Well, okay, now you can unpause and I will supply it for you. So AB is a straight line, right? That's a line segment. Straight lines are 180 degrees, and these two make up that 180 degree angle. We've already said that they are congruent, so we now have two equal angles that add up to 180, meaning each of them has to be 90. I'll explain it like this, so I'll say because angle ADC and angle BDC are a linear pair. Two angles that pair up to make a straight line, okay? So they sum to 180, and that makes, because they're congruent, that makes each of them 90. Okay, so we've got that. So these are now 90 degree angles. So I'm actually going to come in here and change it so that these are now marked as 90 degree angles. And we're basically done. I mean, we are done. So that means that CD is perpendicular to AB, and CD bisects AB because D is the midpoint. Therefore, CD is a line segment on the perpendicular bisector of AB. That's pretty much it, guys. That is why this always works. This has to be on the perpendicular bisector because it has to cross it at AB at a 90 degree angle and pass through the midpoint. So there you have it, and I hope you guys have an excellent day. And let me know if you have any questions or want me to solve any math problems for you. Talk to me about them in the comments, all of that. Like I said, have an excellent day.